So
Okay.
Didier, thank you, Didier.
Thank you, Catherine. Yes, so for the first lecture today, I decided I will go on with the subject I had started yesterday and take time to finish it, and maybe speak a little bit more about this binormal curvature flow in a less regular setting as well, depending on time. And in the second lecture, I will speak about a stability problem. We will see that the difficulty here is the persistence of the concentration of the vorticity. And so there is kind of a baby problem that we try to tackle with my colleague Thierry Gallet in Grenoble for the stability of a linearized Euler equation around a columnar vortex. So the typical vortex tubes that we have been discussing yesterday, but in a straight situation, with the idea that if you zoom sufficiently, then a curved vortex tube looks like a straight vortex. And we'll see that already there were some open questions. Okay, so yesterday I ended with just these two key observations. I did not I did not speak about the proof. I have written them on slides already. The proofs are really short. I just remind you, so what it was about. We have a curve, a family of curves, of smooth curves, say, which solves the binormal flow equation, which I have rewritten here. And I said that a kind of a weak formulation or integral formulation for being a solution to binormal flow is the following, where this means the circulation of the test vector field phi along the curve gamma, and the time derivative of this is an expression where enters into play only the tangent vector to the curve. Okay, there's and of course the test function, but you see we start from an equation which has two derivatives on the curve gamma, and in this formulation only its first derivative, its tangent, appears. So let me just show you quickly the proof of this, because it's only a quick integration by part. I hope you can see it's not too small there, because when I made the slide I had a different screen. I'm sorry. It's fine. Yeah. So I have written here explicitly this time derivative. So first I have rewritten explicitly what it is. So it is phi on the curve dot product with the tangent vector. I use the equation, so ddt. So that's a product, so it will yield two terms. Here I have put the derivative inside the phi. So I have the derivatives of phi and then the time derivatives of gamma. And this one I left it here. And this second term here is when I put the time derivative on this second term. Okay, so I've left the phi and the dst. Okay, and then okay, so what you would normally do here is to expand this time derivative according to the equation. But if you do that, it's too early. So you should not do that at this level. At this level, you only take this s derivative and you reintegrate by part on the other side. You keep the time derivative for the moment. Otherwise, the computation is much longer. So you do that. I integrate by part the ds on the left. So I have this term here, and now I have the ds d gamma. So these two terms are almost the same, except as you see that the ordering between the time and the s derivatives are reversed. So I grouped the two. I let the di phi j here at the start, and now I have a di dt gamma I ds gamma j minus ds gamma I dt gamma j. So this is part of a vector product, and I wrote it in this with the Einstein notation form. So this is corresponding. This is the part of the vector product between dt gamma and ds gamma, which is the third guy in ijk. With respect to permutations. I wrote it in the form epsilon ijk. So this is either 1 or 0. So it's 0 if two of the indices are repeated, and it's 1 or minus 1 if depending on the sign of the permutation from 1 to 3 to ijk. Okay, so you recover this identity, and here again, this with this now is going to be the curl of phi. It's a mixed derivative. So in the end, this expression is the scalar product between the curl of phi and this quantity here. And at this level only, you use the equation for dt gamma. Dt gamma is ds gamma cross product with dss gamma. And now you use a well-known vector identity. So I'm taking well, first, these two vectors, I have reminded here. I told you yesterday that the flow, the binormal curvature flow, is preserving the arc length, okay? And these two vectors here are orthogonal for that reason. ds gamma and dss gamma are orthogonal. So the vector product here is going to be orthogonal to ds gamma and has the same length as dss gamma. And so if I take again the vector product with ds gamma, I'm back to dss gamma. There's no component along ds gamma. So this is just a rewriting of the following. After, now I can integrate by part this ds. I put it back on the curl here, okay? And I have this expression. Just I expand the derivative inside phi, because it is phi composed with gamma. And this is exactly the expression that was written on the previous slides, okay? At the level of Euler, well, no, let me go back to, so that's for the binormal curvature flow equation. And what I claimed yesterday is that for a weak solution of Euler, we have a similar identity for omega. I replace the curve here by the integral against the vorticity little omega. And here on the right, I have the velocity of the field which enters into play. So I mentioned it also. Now, for a weak solution, this can only be given a sense in the sense of distribution, both in time, and I already did it in space. You see, I spoke about little omega here, whereas U is only an L2 solution. So this only makes sense because I integrate against a test function. And so this is the distribution sense of the curl of U. And therefore, the proof of this is really a straightforward consequence of the definition of being a weak solution of the Euler equation. I have rewritten here the definition of being a weak solution of Euler. So you put the time derivative on the test vector field phi. You take a vector field phi, this is classical, which is divergence free, so that the pressure is going to disappear from the equation. And when you integrate against the gradient of the pressure, that disappears. And so you get this, this identity for weak solutions of Euler. Now, this identity is really close to the one I wrote on the previous slide. You just take, so this is a space and time vector field. And the divergence is, of course, only on the space variable. You just take as a vector field the product of an arbitrary function of time times the curl of phi, and phi is the one that appeared in the previous slides. Okay, so there you have the gradient of curl of phi, u. That's exactly what we had on the previous slides. And here you have the curl of phi against u, and you integrate by part, or the definition of curl in the sense of distribution, and you go back exactly to this formulation. Okay, so that's the quick proof of those two identities, but it's really short proofs. Okay. So what remains to be done now? So I recall you, the goal is to relate the Euler equation in an asymptotic setting with these small tube vortex tubes to the binormal curvature flow equation. So now what do we have? We have two identities, I should say two formulations that looks close to each other. So there are at least two tasks to be done now to obtain a statement from these analogies. There are certainly two things. The one thing is that these are different things on the right-hand side. So in some sense, we should find some as mild as possible assumptions on U, okay, on the vector field U, so that this matrix vector field is going to look like this matrix here. Okay, so this is this is a Dirac with value in matrices along the curve. So this matrix on a point on the curve represents the projection on the tangent vector, okay, on the tangent space. And since I have put an identity minus here, I should only prove that this quantity here represent, to get the same thing and this, the projection on the normal to the tangent space. Okay, so that identity minus the projection on the normal will be projection on the tangent. Is it, before trying to do any computation, is it expected? Well, if we go back to our, I would go back, but recall our computations, our heuristic computation from the very beginning, various computations. What we had was that the vector field U, if the vorticity is is an idealized curve, then the velocity was the Biot-Savart law. Was the vector field obtained by Biot-Savart law of a curve. Okay, and what the computation showed was that this vector field, the main part was a field living in the normal to the curve. Okay, and of size 1 over the distance to the curve. It's essentially the gradient perp of the Newtonian potential of a curve. Okay, so it was 1 over the distance, and we showed that by smoothing the curve to a thickness epsilon, well, we should have 1 over the distance up to epsilon, and then you smooth things out. So it is not surprising. Now, when you integrate 1 over the distance, this is a quadratic quantity. Okay, so that would be 1 over the distance squared. You integrate it in the normal plane. The normal plane is 2-dimensional. So you integrate 1 over the distance square in 2 dimensions up to the cutoff value epsilon. This will give you a log. Okay. So what we could have done is, if we take in place of U, in place of the solution of the Euler, the one we would dream of, the velocity field obtained by taking the exact Biot-Savart of a curve and smoothed, we would have the identity. But we don't have that. We only have that U is a solution to Euler. So there will be some work in relating this quantity to this one under the Euler flow. Okay, I will show that just after. And the second thing that remains to be done, because that is not enough. What would be where are we when we show that this looks like this? Well, we have that the relation for the binormal curvature flow at the level omega is almost satisfied. Okay, so it's an almost equality. We would have the equivalent of this plus an error term. Okay? But then we need some stability with respect to such a metric. Okay, because we have an error term, you see, that's going to depend, well, I will show in which norm, but we are dealing with a vector field which is just L2. Okay, so that's probably going to be an error term in a very weak topology. Okay, so the next goal, the next step in order to relate the two is to be able to show that this flow, this binormal curvature flow, has some suitable continuity property or stability property with some sufficiently low regularity norms. We'll see that it is not norms actually. Okay, because if you look at this flow as an equation for a parametrized curve, the level of regularity that you need to control, for example, the Lipschitz constant of the flow associated to this equation is much higher than what you can expect from here. Actually, in terms of Cauchy problem, I did not mention it yesterday, but in terms of Cauchy problem, the well-posedness level for this equation is H3, so 3 derivatives in L2. This is much higher than what we can hope here with just having the tangent vector. Okay? So that will be the second thing to do. So I will first speak about relating this to this, and this is the work of Gérard and Zeiss, which I mentioned yesterday. And the second thing I will discuss is the continuity of this equation in low regularity, and this is work by Bob Gérard and myself from 2012 or 15, I don't remember. Okay, so let me give you a statement first. The end statement, because in the end, that's what we wish. Okay. So the theorem, because I spoke for too long now, I need to give some, so I said it's Gerard Zeiss, but the one I'm going to state is a weaker version, but it's maybe easier to understand and easier to discuss. I'll mention later. So we are going to consider a family of curves, gamma t, smooth curves, smooth closed curves. They do not satisfy an equation at the start, and a solution of Euler. I take solutions, weak solutions, L infinity, L2, to Euler 3D. And I'm going to make a number of assumptions. And the conclusion in the end will be that necessarily gamma t is evolving according to the binormal curvature flow equation that I wrote in the previous slide. So what are the assumptions? The first assumptions is that U epsilon is conservative. Okay, we are dealing with weak solution of Euler, so this is not a guarantee, it's conservative. Conservative. Okay, the second assumption is that the length of those curves gamma t has to be constant. Let me call it L. Then I need to suppose something about the energy, the kinetic energy of the flow. So I write it in space, U square in space. So at time 0, but I assume it's conservative, so it's at any time. And I'm going to assume that my initial state had not too much energy, too much kinetic energy with respect to the minimum energy required to build a vortex tube of length L. Okay. And from our heuristic computation, we know that this energy, this is the one I mentioned just before without writing anything, where there was a log appearing. This energy should be like log of the thickness of the vortex tube times the length, of course. And we are going to assume, well, this is only an order 1 computation because it depends on the actual shape of the curve. So at first, this is the main order. The second order will be order 1. So there's no advantage well, there's no sense to put something smaller here than order 1. And we will actually put order 1 as epsilon to 0. So I consider sequences of solutions. That will be a theorem for something asymptotic. So this is an assumption. This is an excess energy assumption. I assume that the excess of energy is not too big. The next assumption is a localization assumption for the vorticity. And that's we say talon d'Achille in French. I don't know how you say Achilles tenderloin, you say in English, I don't know, of the theorem is that the assumption on the localization of the vorticity has to hold not only at the initial time, but for all time considered. Okay, I'm writing this, I'll mention this norm later. Okay, so that's something measuring the distance between, recall, this is my idealized vortex filament. That's how I called it yesterday. So this is the exact curve, okay, the Dirac along the curve, and this is my vorticity. And so I assume, we said we have tubes of thickness epsilon, so I'm going to assume that this norm, I will mention what it is exactly before, and not only at time 0, but uniformly in time, in t, so let's say in some fixed interval of time, 0 capital T. Okay. So the big question next would be to try to prove that if such things hold at time 0, it perturbates in time. But this is a very difficult question. And so this is localization. We also have to assume some geometric property of the curve that gamma t has no self-intersection. You don't see self-intersection when you look at the equation in a parameterized form, but for Euler, if you want to approach this with fields, it will certainly feel the fact that the curves would self-intersect itself. So gamma t has no self-intersection. Again, for all t. But this is less of an issue because it's for the limit flow. So you can at least restricting time. If it's true at time 0, it's true for some time. And then, as I said, then gamma t necessarily solves the binormal curvature flow equation. Okay, so this is certainly a very reasonable assumption. That one I'll discuss maybe that later. It's not completely obvious that it should hold for limits of solution of Euler. Actually, in the physics literature, some people claim that there is some that the length of filament should grow, but it's not clear if the time scale at which such phenomenon should appear would be seen in this asymptotic. So I consider it a very reasonable assumption. That one as well. That one is certainly reasonable also, but as I said, the goal would be to skip this uniformity in time and only transform it into an assumption at time 0, because of course you assume something a posteriori on the solution. And that one is also certainly very reasonable. So this norm here, this weak norm, the localization assumption, by definition, let me just call it for a vector field omega, say in L2, or even less than, well, if it wasn't a vector field, it would be the dual of Lipschitz. But it's on vector field, so you don't take the full derivatives on the test function, but only its curl. So it's the supremum of omega against phi, when the curl, so phi is a test vector field, and the curl of phi is less than 1 in L infinity. Okay. So this is the definition. It's called the flat norm or homogeneous flat norm, because I don't assume anything on the L infinity bound on phi. So there's a very nice interpretation of this norm when omega is a curve. Okay, or say when omega is two curves. So if let me draw a picture here to get an intuition of what this localization means. If you take one curve here in space, so that would be a omega 1, okay, oriented this way, and I take a nearby curve here in space, okay, that would be omega 2. Then the flat norm of omega 1 minus omega 2 is actually the area. It's the area of the minimal surface joining the two curves. Okay, let me try to draw it this way. I'm very bad at drawing, but you can understand. It should be clear like that. So you take the smallest surface area that whose boundary would be the difference between the two curves. Okay. So that's what this norm measures. Okay, so that's the theorem. And okay, let's go to, well, no, let me mention, the theorem is actually, their theorem is actually stronger than that, in the sense that the curves here are not supposed to be smooth. They can be much wilder than that, not too much, but much wilder. And it's also not a theorem where you need to pass to the limit as epsilon goes to 0. I stated this way because it's much easier to understand, to read the statement, but it's actually a quantitative statement for a fixed epsilon. Okay. Okay, so some ideas. As I told you, sketch, oops, there are two things to be done. So the first, as I recall, the first thing was to relate identity minus U wedge U tensor U over K epsilon to tau wedge tau. Okay, and we said it would be true with our idealized vortex tube. So it's a point of putting a man in the middle. Put a man in the middle. I'm going to consider V, which is obtained by taking Biot-Savart, and I take the exact curve, okay, omega gamma, and we smooth it out a little bit. So rho epsilon times this one. Okay. So this was our idealized smooth vortex tubes from the very first slide, the one for which we did all the formal computations. Okay. And we just put it in the middle. So the formal computations tell us that if I replace here the U with a V, we are very close. Okay, we are already sufficiently close. So in the end, what's important is to compute. What we wish is to compute the difference between this one and this one. Okay. Okay. So let me just write it in this form. So these are two matrices. I'll just consider components with components, and it's the usual. I take the difference between these two, ui uj minus vi vj. I'll try to show in this computation where the flat norm is going to appear and why it's important, and where do all the assumptions come from, why these are natural assumptions. Okay, so let me write it. Let me rewrite this quadratic form in this way: ui minus vi, uj minus vj, plus ui minus vi against vj, and there's the symmetric one, plus uj minus vj against ui. Okay, so we have three terms. All of these appear against the test functions and blah, blah, blah. But I'm not going we are not going to use the structure of that test function. It was a gradient of a curl of phi. Here you just, it's not important. You just view it as a test function. We're not going to use any structure there. Okay, so there are two terms. There is this one and this one. Okay, the third one is exactly like the second one. So I will take this first, term first. And for this one, I'm just going to make a quadratic computation. So I will have more than that. I will even control the difference of U minus V in L2. Okay, the kinetic energy of the difference. And here I just write it as U squared over 2. Minus, I take a minus V squared over 2, and then I have plus V minus U. Okay, so some of the assumptions are going to control me this already. Okay, recall, what did we say? We said that this comes into the definition of the excess. I told you that the energy, by assumption, the kinetic energy of U should not be bigger at O of 1 distance to the best energy I can hope to build a vortex tube. Okay. In particular, I was capital O of 1. I have no more capital O than capital O of 1 more kinetic energy than this guy, than this perfect guy. Okay. So this is less than capital O of 1. And so I remain with this one. Let me go to the next slide. That's where or maybe I can do it here. That's where the flat norm is going to appear. Let me do this very nice trick. So V, we call V, was Biot-Savart of rho epsilon convoluted with the curve. So Biot-Savart, let me write it in this way. It's curl of Laplace minus 1, like in Elgin's talk, of rho epsilon wedge my curve, omega gamma. Now I integrate by part this curl. It is on V, I put it here. Okay, so it's going to be the integral of Laplace minus 1 of rho epsilon against omega gamma times curl of V minus curl of U. Okay, and maybe I still have room, like in a blackboard, to do this nasty thing here on the right. Now I use the definition of a flat norm. This is less than the flat norm of this, because I have control on the curl of this. This is less than the flat norm of curl of V minus curl of U times, so the flat norm, I recall you, it's the L infinity norm of the curl of the test function. Okay, so the L infinity norm of the curl of Laplace minus 1 of rho epsilon wedge omega gamma. Okay, in L infinity. But this again, this is V. Okay, I have taken the curl out, integrate by part, and then use the definition of flat norm. So this is V. Okay, and so this by assumption, so not by assumption, curl of U, that was the localization assumption, it was epsilon closed in flat norm to the curve. V as well, because V is our idealized vortex. So this is less than epsilon. And V, what is V in L infinity? Well, V was our, again, it's our perfect vector field. So it's 1 over the distance to the curve up to epsilon, up to the distance epsilon. So that one is epsilon minus 1. It's explicit, that V, it's almost explicit. And so again, this is an O of 1. And that's it. Okay. Time is running. So we still have the second term here. Well, believe me, or believe Bob, the same kind of trick work, and you get an O of 1 at this level. And so if we come back here now, where was that? It was here. Now we have O of 1 closeness of this to this one. So when I divide by this log, I have a O of 1 over log. So I'm close, and that was the goal. So now the second step to be done is to obtain some stability for this equation. Now we forget completely about Euler for some time, and we are just interested in a stability for this equation. Okay, so let me do the following. I have take my notes. I'm going to introduce, so the step 2. So it's stability for BF. Stability in low regularity. So I'm going to consider a smooth curve gamma, an arbitrary smooth curve for the moment, gamma. And I'm going to consider then a second curve, maybe much rougher than gamma. Let me write it in this way, but close to. Okay. And I want to measure somehow how close this green curve is to the blue curve. And to do that, I'm going to consider a vector field. So when I take a point here on the green curve, I'm going to consider the closest point here on the blue curve. If the two are sufficiently close, then the blue curve, it has a nice curvature. So if I'm at a distance less than the inverse, than the max of the curvature, I have a unique point projection, blah, blah, blah. So I can consider this point. I take the tangent vector to the blue curve, and I'm going to reproduce it here, but with a fade out which depends on the distance. Okay. So I'm going to no, so I explained it with the drawing. Now I'm going to write a formula. I'm going to consider a vector field capital X on the whole space, defined in this way. X, this curve maybe then will depend on time, but at this level, let me forget about time at this level. Gamma X of F is, as I said, a fade off of the distance from the point X, distance square from the point X to the curve gamma. So this is a scalar, and I multiply it by the tangent to the curve gamma at the closest point. I call it P of X. Okay, so this would be X, and this is P of X. Okay, and F, as I said, is just a cutoff function. So the precise one is F of D square is equal to 1 minus D. Let me put an R naught here. Square to the third. So that's if D is small, if D is less than R naught, and 0 if D is larger than R naught. So what is this R naught? Is this this security radius where you have a unique projection point. Okay, so this R naught should be smaller than the maximum of the curvature of the blue curve. Okay, it's the tubular neighborhood where all this is well defined. Okay, so in particular, this vector field is compactly supported. As soon as you are at a distance R naught from the curve, you are 0. And I'm going to measure the distance between the two just by taking this integral. Now I consider the energy, well, not the energy, say, let me call it E, but it's, we call it F in the paper. If my, let me give it a name, this function, this green one, let me call it lambda. The distance between lambda and gamma, or the closeness of lambda to gamma, because it's not a symmetric, it's not symmetric. You see, the vector field, I built it with respect to the smooth. So the excess of lambda with respect to gamma is just the integral along the rough curve of 1 minus x scalar product with the tangent to the rough curve. Okay. So see, this vector field is less than 1 in absolute value. It's a tangent vector multiplied by a function which is between 0 and 1. So this thing here is pointwise positive, non-negative. Okay? So this is certainly positive. And what can you say more? If you analyze this, you can easily verify that this guy here is pointwise larger, maybe up to a constant, to the distance square between x and gamma, and also to the difference between the tangent. So the tangent to the rough curve and the tangent to the smooth curve, but not at the same point, okay, at P of x. And this easily follows, you just expand this scalar product at the first order, and you have these two. So what is this? What does that measure? It's a kind, if you see, it's a kind of H1 measure between the two curves. You see, there is a distance squared and a square of a difference of tangents, so of derivatives. So it's some form of H1 norm, except that it does not arise at the same point. These are about two objects in space. Okay, nowhere, as you can see, nowhere the parametrization of gamma or lambda is in the computation. It's a geometric quantity. Okay, but it's positive. It's non-negative. And if both curves are really close, so it controls the Hausdorff distance, for example, between the two. And the stability estimates, which we prove, is the following. We have, so that's the key lemma. That's from, so as I said, that's Gerard himself. That appeared in two places, is the following. If both gamma and lambda solve the binormal flow equation, then there's a Grunwald inequality on this quantity. So d dt of E gamma of lambda is less than a constant which depends just on gamma, so just on the smooth curve, times E of E gamma of lambda. Okay, where as I said, C lambda just depends on the first one. And let me explain you the reason for this, and I will finish with that. Okay, so recall that there's two things. If we only know, if we know that the rough one, well, the rough, then say the non-reference one, then what I call lambda solves the binomial flow. Then we add these weak formulations. So ddt of E gamma of lambda was, yes. So up to this constant here, okay, this is exactly the form of the weak formulation for binormal flow. See, it's the circulation of a vector field along the curve. Okay, so we had a formula already for this. This is the integral on lambda. Well, here the vector field is depending on time, so I have to add the time derivative of the vector field. It's just come in addition in our prior formula, plus gradient of the curl of the vector field x. So x is the vector field attached to the reference curve. So maybe I should call it x gamma. Okay, it's built upon gamma, and the tangent to the rough curve. The tangent to the rough curve. Okay, so this is just using the fact that one of the two solves the binormal flow. Now, the second fact, actually the key lemma comes from the following key observation, is that now if, on the other hand, if gamma solves the binormal flow, then pointwise, we have the following, that this, it's an equality about the vector field that I just built, this capital X, and this test vector field, minus dt, what enters here into play, dt x gamma against an arbitrary unit vector plus gradient curl of x gamma psi psi. This quantity, pointwise, is less than a constant, which again only depends on gamma, times the quantity I wrote before. So the 1 minus x scalar psi. And this holds for any unit vector. So you see the conclusion comes from two totally distinct things. This formula comes from the fact that lambda solves the binormal curvature flow equation, the non-reference one, and this estimates only come from the fact that little gamma solves the binormal curvature flow. But here I could put any unitary unit vector field. It doesn't have to be the tangent to the rough curve. So the conclusion comes from two independent facts, and the proof of this. It's a long proof, but it's I mean it's a completely it only uses the definition and the fact that little gamma solves the binormal curvature flow equation. So I refer you to the paper for that. But maybe the intuition for how did we came with this vector field? Well, first, as I told you, it is a natural. Vector field to try to measure the distance between curves when you have no parametrization between these two curves. Okay, so this is a natural vector field, And the other remark is that in the parts which I did not present yesterday, but in when you study, for example, point vortices in 2D, the work of Marchioro and Pulvirenti, which have studied the point vortices or the spreading of highly concentrated vorticity in the plane. One function that plays a key role is the square distance function to the vortices. And because you use, for 2D Euler, you have the conservation of the angular momentum for one vortex. And when you have many vortices, you can put some square distance functions to each of the vortices and try to do some computation with that. And in a sense, you see this, test vector field may look like a three-dimensional equivalent to this square distance function to the vorticity measure. It has a decay like the distance squared, but it's a vector field, and so we take the vector field aligned with the best vector field to the okay. And once you have these two instruments, the proof of this theorem is almost finished, because what we using this analogy, because now we have closeness of the forcing terms and stability of the flow. And when you have both, you understand that that's enough to get convergence of the flow. Okay. So I think I'm almost okay on time. Maybe since I have 3 minutes, I can chat for 3 minutes and explaining. Well, I can first, yes. Where is that? To introduce the next lecture. As I told you, the difficulty, well, the one thing that one would like to improve in the statement of this theorem, or to weaken, is this localization assumption. They have to assume that the vorticity localization holds for all time. And that's also a question about stability of the vortex tubes. This is the missing ingredient. Is some form of stability of the vortex tube, of these little vortices. So in the next hour, what I will do is take a straight vortex. Okay, when we have this curve, you take a little piece here and you zoom in, because the thickness is epsilon. Now you go back to scale 1, okay, and but then the curvature will be 1 over epsilon, and so when epsilon is small, you get a straight vortex. And so the next question that I will address in the last lecture is trying to understand if we can prove some form of stability, or at least prove that there is no unstable mode for such objects for 3D Euler. Okay. I thank you. If there are questions. I don't see there's a chat somewhere.
It doesn't look like there are any questions in the chat, but if folks want to unmute their microphones and ask their questions verbally, you're welcome to do that now.
I have a question, Didier. In your last slide, you discussed the stability of this BF flows, but the two curves, gamma and lambda, they did not have the same role, right? One was a kind of smooth one, and the other one.
Yes. So this is not. Yeah, you are completely correct. I should have stated differently. It's not a stability of the flow in a low regularity space. It's a weak, strong stability result. So we assume that we have a weak, a smooth solution for which we control sufficient norms, actually up to 3 derivatives. and we consider a low regularity solution that starts close to it. Okay, that estimate, you see, the constant, where is it? The constant here depends on high norms on gamma, but it does not depend at all on lambda, this constant. So these estimates will give, in particular, weak strong uniqueness.
So this key lemma gives an estimate of how close these two curves.
Yes, but one of them has to be smooth and controlled. So it's a typical estimate for weak strong stability or weak strong uniqueness, if you want. But it's not. It does not give stability estimates for two weakly regular curves. Otherwise, we would have an existence and regularity at such a low level, but we don't have. Still, these estimates allowed us to, in the first of the two papers that I mentioned in 2012, to give a meaning and to have an existence theorem for curves that are no better than Lipschitz. Okay. Even a bit worse than that. But in particular, curves with corners, whereas the equation has two derivatives. But for a curve, for a square, for example, we have an existence theorem. Okay? No uniqueness, but we have an existence theorem and a weak strong uniqueness. There has been a lot of work by Vega and Banica, my colleague Valeria Banica, to try to understand better this, the evolution, for example, of curves with corners, in particular the square that I mentioned before. When we did that with Bob long ago, we had some numerical computation showing some very strange phenomena. When you start from a square, it looked like at sometimes it would reproduce the square or a figure with 8 sides and so on. And now the conjecture is that if you start from a square, for example, at rational times, it would be a polygonal line whose number of sides depends on the rationality of the time. Okay? And at irrational time, it would be a fractal. That's the conjecture that they are trying to establish. So it's still open, but they are progressing. So it's just to say that this binormal flow is really an appealing one. I did not mention also, but this equation, the binormal flow curvature flow equation in parameterized form is has an infinite number of conserved quantities. It's actually an integral equation. But that doesn't mean it's easy to compute the solution as you said.
Thank you. Well, thank you, Didier. Let's have a little break until 11 or something, and we'll get back in a few minutes.